want to acknowledge Jed Brown, Matt Nepley, Carl Rupp, and Barry Smith for their contributions by providing slides for this tutorial material that we're presenting today. This is really just a glimpse of some of the functionality within PETSc, presented at a rather high level, given our time constraints. But I encourage you, if you identify a particular aspect that's of interest to you and you want more information, please go to the website here and you'll see there's a variety of other more in-depth tutorial material and also examples. So we can help, Satish and I can help guide you to where to look for further information. So today, we're going to follow this outline where we'll first talk a bit about the philosophy of the software package overall and our design and our approach for achieving good performance on extreme scale machines. We'll then talk about the fundamental data objects used in PETSc, vectors and matrices. And upon those data objects, we'll then build to discuss linear solvers, in particular Krylov subspace methods and preconditioners. We'll talk about nonlinear solvers, and then building upon that, time-stepping methods. We'll also discuss optimization solvers within the tau component of PETSc. Then, if time permits, I'll talk a bit about various support we have for handling topological abstractions, in particular through the Distributor Ray component. That the concepts handled there are important, but yet takes a lot of time to go into them in depth. So that might be an area where we discuss things offline or refer you to other areas for more information. And then finally, Satish will talk about using debugging and profiling capabilities in the library to help understand performance. So first of all, it's important to note that the PETSc software package is really intended as a platform for experimentation. We want to enable it to be very straightforward for not only ourselves, but the community to use our software to experiment with models, with different discretizations, different solvers, and different algorithms. And of course, the boundaries between those are very blurry. The book shown here, Domain Decomposition, was written by Barry Smith, Petr Bjorsad, and Bill Gropp. The reason the PETSc library started is because Bill and Barry were trying to collaborate and share information about domain decomposition algorithms. But at the time when they started in the early 90s, there really was no software available that enabled it to be easy for them to do that. So that is what spearheaded the development of the PETSc software package from the start. And I joined them to work with them in 1993. They started doing PETSc capabilities in 1991, and we've been continuing thereafter. PETSc stands for the Portable Extensible Toolkit for Scientific Computing. By portable, I mean that we aim to run on a variety of different kinds of architectures, including extreme scale machines that are the emphasis of this program. But we also are very committed to supporting the whole range of software architectures and machines, from individual laptops through small clusters of workstations and whatnot. In fact, many people do most of their development on those kinds of machines, and then only at the later phases of their work run on the extreme scale machines. So that whole spectrum is very important to us. We support a range of different operating systems. The software is usable in C, C++, Fortran, and Python. We support a variety of different precisions, both real and complex arithmetic. We support solution of up to very large system sizes with billions of unknowns, with very good scalability. And again, emphasizing that the software is free to everyone to use. We have a BSD style license, so we encourage people to use the software, and also we follow an open development model, so many people in the community contribute to the software, and we invite any of you who have interest in doing that also to do that. Our website provides information for how to proceed. So the toolkit really emphasizes extensibility. As I'll explain with the design of these various objects, really the intention is that everything has a so-called plug-in architecture, so that in addition to the functionality that's already in the library, someone else can provide additional implementations, and then they'll be available for use using the same abstract interface. So an example where that might be interesting is, for example, if a vendor wants to supply a particular implementation, then that would be available to users. Our approach here, being a toolkit, is that we provide not only algorithms and implementations of those, but also some capabilities to help with debugging and low overhead profiling. And Satish will explain some of those near the end of the presentation. We really do emphasize composability. As Lori mentioned, there's lots of different aspects of solving problems, and it's important to be able to combine different algorithms and data structures together to try to compose things together to handle especially the large multiphysics problems that are of strong interest on extreme scale computing. We know that it's impossible to select the best algorithms and data structures for your problem a priori. So we really emphasize exposing what we call an algebra of composition, so that you as a user can pick and choose from among various capabilities and then can experiment and refine as you move along. So the solvers are designed to be considered in some senses decoupled from the physics and discretization. So you can use whatever mesh management and discretization infrastructure you would like to use, and you'll hear about some of those from our collaborators in FastMath this afternoon, and then you can interface to PETSc for the solver aspects of what you're doing. The toolkit is used by a wide range of computational scientists. This slide just provides information on a few of those projects that are built upon using PETSc. And I want to emphasize that there's many tutorial-style examples provided with the library for the various aspects of functionality through the website. It's very easy to explore and to find working, running code for many kinds of problems, and then it's possible to start, for example, using that code in your context, your special context, by replacing some parts of the existing working code with other parts that would be unique to your implementation. So it oftentimes gives a very effective starting point for working on new applications. So this infrastructure is intended to make it easier to experiment and develop new capabilities, but we still need to acknowledge that working on large PD problems is a very difficult endeavor, and so the PETSc software is not a silver bullet, as stated by this quote by Barry Smith. So many of you may know that Barry is the lead developer of PETSc, and he's really the spirit that has continued to provide guidance for the project overall. We have contributions from many people in our development team and through the community. But Barry really has provided a lot of sustained guidance and design. So it's possible to obtain PETSc by using our Git repository. You can also download a tarball if you like. And once you download the package, you can configure it with various options, including installing some of the external software that we talk about today. So it's possible, as shown here, to configure the software so that you could download and install ML, Hyper, and SuperLU, some of the other complementary capabilities provided in FastMath, software developed by our friends at other institutions, so that you can experiment with different algorithms at runtime. So most of these external packages can be automatically downloaded and installed at runtime. Here's a partial list of functionality. This certainly is not a complete list, but it's intended to be a way to make it a bit easier to use tools developed by different groups. So as I mentioned, we use a Git repo to manage our software. This is a graph that shows the contributions to the repository from 1994 through 2016. Basically just showing we're a very active project with many contributions, and we welcome yours. This diagram shows the structure of the PETSc library overall. It's organized in a way that is consistent with how many algebraic solvers are organized. That is, we build on top of computation and communication kernels at the lowest level. I know you've already heard lots of great information about MPI and other communication facilities. Those are our foundation. We use those. Built on top of that, we have a very lightweight profiling interface that understands the various objects and design of the library that can help application programmers understand how their programs are organized and where the time is being spent throughout those. Layered on top of that, we have the data objects that are used for distributed computing for matrices, vectors, and also index sets or indices. Indices indicate particular items within a global problem that would be local to certain processors. As Lori indicated, when we're dividing problems across multiple processes, we need to determine how to communicate from one process to another, and index sets are a way that we help to handle that in PETSc. Built on top of that, we have linear solvers, which consist of Krylov subspace methods and preconditioners. On top of that, nonlinear solvers, which typically require the solution of linear systems underneath. Not always, but often do. So there's some that would work directly just with vectors and matrices. As a peer with that, we have optimization software in the Tau package that likewise also builds on the linear solver capabilities. And then on top of all of that, we have ODE integrators, which can then interface to the nonlinear solvers and linear solvers and whatnot as needed. So during our presentation, we'll talk about how these various aspects of functionality work together. As I mentioned, our libraries are written in such a way that users don't generally have to work directly with MPI. So through these data objects and algorithmic objects, you as a user can rely on those to handle a lot of the interprocess communication that's used. The algorithms, as we write them, are what we call data structure neutral, and they access the communication through the objects for vectors and matrices. This diagram shows how one might think about interfacing between code provided by the application or user, as shown in blue, and code provided by the PETSc library, as shown in the intermediate green box and the sub-boxes within that. So typically, we would see a user's application interfacing with time-stepping code, which then internally would use whatever capabilities are needed for nonlinear solvers, linear solvers, and whatnot. And then from within the nonlinear solvers, for example, the package would then provide control back to the user for things like evaluating a nonlinear function where you're doing the real meat of your work to describe the physics of your problem. And likewise, also evaluating a Jacobian if you're choosing an approach that needs derivative information. So we'll describe in more detail how we handle going back and forth between those various layers. So for each PETSc program, you begin in your application space by initializing PETSc. And this really just gets our data structure set up. It can determine setup for MPI if that hasn't been done already. And you can use whatever subset of processes that you find appropriate for that aspect of work. So we can either run across all processes or across a subset. You might be using another subset of processors for something else. At the very end of your program, you call PETSc finalize, which will calculate a logging summary. It will shut down and release resources, and then depending upon what options you activate, it can help to check for unused runtime options, memory leaks, and whatnot. Each object, or each layer of functionality and object has a basic interface as described by this slide. So conceptually, whether you're working with a nonlinear solver or preconditioner or whatnot, you create the object. You can name the object, set the particular type of object. You can set an options prefix that would enable you to tag that particular object in order to set runtime options unique to that. You can provide customization from the command line, setting runtime choices, for example, for convergence parameters, whatnot. You initialize the object through the setup call. You can view the object to understand the details of what's happening inside it, and finally destroy it when you're done. So all of the objects support this basic set of functionality, and they all support the help option. So let's start now with vectors and matrices. So PETSc vectors are fundamental objects that represent field solutions, right-hand sides, and other kinds of functionality that makes sense to store in a so-called vector. Each process in a parallel setting locally owns a subvector of contiguous global data. So the commands for creating vectors are shown here. You do generally a global creation command. You can set the size that's owned by each particular processor. You can choose a particular type of vector and set various runtime options. So from within that vector, you, as a user, can directly access the memory. You have direct access to the values. You can do various vector space operations, such as dot products, norms, whatnot. And there's functionality to help communicate automatically when doing parallel assembly. We'll talk a little bit more about that in the next slides. Also, there's custom communication available for scatters between different vectors. So again, this is just emphasizing the concept of collectivity in parallel. MPI communicators specify the processes that are involved in any particular computation. And so that is indicated at the time when you create a vector or any other object. And some options and some operations are collective, such as doing a norm, for example, and some are not collective, such as getting the local size of a vector. So if you're doing sequences of collective calls, they must be done on each process in the same order. The way we assemble parallel matrices and vectors is quite flexible. So processes in general can set whatever entries they want to set. They don't need to set only those that are owned by their local part. And PETSc will automatically communicate data as needed if that is necessary in an assembly phase. So in more specific terms, for the case of vectors, there's a three-step process. So in this case, on each processor, code would either set or add values to a vector, would initiate communication to begin sending values to other processes if need be, and then complete the communication. So that's done by these sequences of calls. So vec set values indicates whether you're either inserting values into a vector or adding values. Typically, for example, if you're doing a finite difference discretization, you'd be inserting values. Oftentimes with finite elements, it's more natural to use add values where you're building up contributions from particular elements. And then after that phase, we do the vec assembly begin and end in order to do the communication that may be necessary for vector entries that are not assembled locally. So here's an example of one way to set the elements of a vector. In this case, we determine the local size of the vector, and we determine the rank of our processes. And here we're saying if our rank is 0, then we will set values for our whole vector, and then we'll call the assembly routines. So this is a simple way to get started with a program, for example, maybe on the first day when you're writing some code. But as we can all tell, it's not a good choice over the long term because, for example, if you have 1,000 processes, 999 of them would be idle. Well, process 0 is setting values into the matrix, or into the vector rather. So in general, a better approach is to have each process set the values for the segment of the vector that it owns locally. And that's what's shown here, where we're determining the ownership range of the segment of the vector for each process and having each processor do its own local part and then finalizing the assembly. Now this approach looks very straightforward and simplistic, but it really doesn't acknowledge what happens in most codes, where in most codes there are typically some values that are not locally owned. As shown in this diagram here, when we're discretizing, we need to compose, for example, a mesh across multiple processes, as represented simplistically here for both a structured case on the left and an unstructured case on the right. And typically, when assembling values, for example, to compute the nonlinear function for a physics problem, you would be looping in your user-provided code across the segment of the problem that your process owns. So in a finite element sense, you would own a segment of elements for each process, such as those shown in the red dots. But as you're computing, you would need information for neighboring nodes that are actually stored and owned by other processes, as shown by the blue dots. Those are often called ghost values or ghost nodes. So during the assembly process, what can happen is you can assemble based on what is natural for you with your partitioning, say, of finite elements, and any entries that are not owned locally by you would then be communicated during the VEC assembly begin and end stage, and they would end up where they need to be. So you don't need to worry about that explicit message passing. Now, the part of the PETSc software package that helps to deal with this transitioning between sort of local and global views of meshes is the data management part of things. And that I will talk about, if we have time, towards the end of the presentation. So basically, we just have capabilities that can help to automate the transition needed to go between these local and global representations. So sometimes it's more natural for you as an application to work directly with the locally owned arrays of your vectors, and these capabilities are possible by directly accessing the arrays. This doesn't do a copy, this just gives you access to the data in your vector array through vetGetArray. Then you can add values or modify values, and when you're done doing that, you indicate so by calling vec_restore_array. That makes it safe so that you as an individual process can modify elements and then notify the rest of the computation when that is finished. So matrices work in a way that's similar to vectors. In general, a matrix is a linear transformation between finite dimensional vector spaces. And by forming or assembling a matrix, what we mean is that we're then able to define its action in terms of entries of the matrix, which typically is stored in a sparse format for PDE-based problems. In PETSc, you create matrices and use them through this sequence of commands. You first call mat_create to indicate the processes involved in the computation, set the various sizes for the locally owned parts, determine the type, set a variety of options, and optionally you can pre-allocate matrix memory, which in practice is very important for good performance. Can determine block sizes if you have multiple degrees of freedom per node. That's a very important aspect for performance. And likewise, then you can do mat set values, which is analogous to the vec set values. So there's a single user interface for matrix functionality, but multiple underlying implementations. So a common one is what we call AIJ, it's storage by the non-zeros per row. There's block variants of that, symmetric variants. There's also dense storage formats and so-called matrix-free matrices where the actions of the matrix on a vector are defined, but we don't actually store data for the matrix entries themselves. So an important concept is the matrix in our view is defined by its interface, not by the specifics of the data structure that are used for storage. This diagram here shows the way we split parallel matrices across processes. So each process owns a submatrix of rows, as indicated here, where we have 6 processes. And in practice, the storage is broken down by a diagonal blocks, which are shown in blue, and the off-diagonal blocks. So when we're working on assembling matrices, this is sort of the layout that we mostly use. We're not going to go in detail through matrix assembly. I'll just say that it is a similar approach to what we described already for vectors. That is, loop over parts of your rows and insert matrices. So this particular example is showing how you might do this if you were inserting all entries from the rank 0 process, which might be a good way to get started when you're first doing an application, but of course it's not what you want to do over the longer term. This other slide shows what you really want to do is generally loop over the segments of the global problem that your local process owns. and set values. So an advantage of this approach is it's much more scalable, and the code still is quite straightforward and simple. Similarly to, as we described for vectors, the mat assembly begin and end phase handles any communication that would be needed. So you're not required to set every single entry locally on the process that owns that subblock. And in practice, most application codes do need to transfer some data during the mat assembly and begin and end phase. But you as an application programmer aren't dealing with the details of those MPI calls. That's all handled within the matrix assembly begin and end. So next we'll talk about iterative solvers. Those build on top of the vector and matrix data structures. We talked about some matrices having explicit storage and some not. Even if you don't explicitly store a matrix, you can still do Krylov iterative solution methods. Jim talked about those earlier today. The key point here is that we build up Krylov subspaces through matrix vector products. And because of that, we only need to matrix to provide that functionality, that is the matrix vector product functionality, in order to be able to write a whole variety of algorithms that are Krylov methods. There's no way a priori to know which particular Krylov method will be most effective for a given problem. Our approach in PETSc is to, through this simple interface, provide access to many different algorithms. So in order to activate the Krylov methods, if you're working directly with a linear solver, you simply set the operators that you want to use by calling KSP set operators. This indicates the matrix that defines the linear problem you want to solve, and optionally a different matrix to use as a preconditioner. We'll talk more about preconditioning in the next slide. And then we call KSP solve to solve that system, where you indicate the vector of the right-hand side and also the solution vector. And from that, you can access the preconditioner, and you can change to activate a variety of different algorithms on the command line. So this slide shows a range of some of the solvers. We don't have time in this particular tutorial to explain the theory behind all of these, but some of the slides online do explain the algorithms in more depth for those of you who are interested in more details. I'll just mention that the GMRes family of algorithms is often used in practice in many problems. It's our default solver, but there are many others that are available. The green link line there, if you click on that in your PDF file, it will give you a hyperlink to a table of all the solvers that are accessible and available through the PETSc libraries. So preconditioners can be incredibly important for the practical use of Krylov methods for many problems. So the idea, Lori introduced this, is to improve the convergence of the Krylov method by applying a preconditioner to the problem. So that is, we use another matrix as represented here by P, where the product of AP is more amenable to convergence than just the original matrix. So in practice, we don't typically form these products of matrices, but rather we apply different algorithms to use the operator, the inverse operator of the matrix through the preconditioner. So oftentimes, applications will use a preconditioner that is slightly different and cheaper somehow than the full linear operator that defines the problem. And figuring out the exact way to do that most effectively for a given problem is really an art. There's lots of problem-specific information that can help make good choices for what to do. And some of our other speakers today will talk about that. So this is a list of various preconditioners that are available in PETSc now. Jacobi is the simplest. I'm sure many of you have already become familiar with many preconditioners. Jacobi is just diagonal scaling. Block Jacobi is conceptually the same thing, but extending to blocks, and that's often a first choice for preconditioners in parallel because it's very simple to understand. SOR, additive Schwartz, incomplete factorizations, multigrid, physics-based splitting, approximate inverses, substructuring, and matrix-free approaches. So Again, we don't have time to go through the algorithmic theory of all of these, but I encourage you to listen carefully when Rob Balgoo and Sherry Lee and other people speak later this afternoon. They'll talk in much more depth about what the algorithms are and how important it is to make good choices for algorithms and implementations. Just like to emphasize the so-called matrix-free approach here means that you as an application can provide preconditioner functionality that just adheres to our object interfaces, but is implemented in some specific way that exploits problem-specific information. And so you can then more easily provide what makes sense for your problem, but also have the flexibility to experiment with and compare with this range of other functionality that's in the library. So we don't have an opportunity to explain multi-physics type preconditioners in detail, but since this is one of our newer aspects of functionality and it's very important for problems, especially as we're scaling up to extreme scale, I wanted to just emphasize our field split type of preconditioner, which is intended to make it easier to tackle problems where you don't necessarily want to treat your whole global problem as one, but you want to exploit the fact that you understand you're bringing together multiple parts that come from different physics or different aspects of modeling. So we support a variety of approaches here. There's more specific information online that can provide details about that and also some examples that explain how to use it. So part of what is important to emphasize here is that we have the ability for codes to compose different preconditioners, including composing block preconditioning and multi-bridge preconditioning as needed. And so this custom choice of putting together different kinds of algorithms can happen at runtime by activating command line options. And the code does not depend on specific details of the matrix format or whatnot. So there's a lot of flexibility. Now, built on top of the linear solvers, we have nonlinear solvers. This is a list of the methods supported in PETSc now. Basically, in addition to the methods listed here, you can also define a shell nonlinear solver, which can be whatever you as an application person want to implement. The SNES component is our nonlinear solver component, where the runtime options can be provided by the application to make choices for the type of solver, the convergence tolerances. You can activate various kinds of monitoring so that you can monitor convergence, view the details of the algorithm, et cetera. And this same kind of approach applies also to the lower levels that we just described, that is to the preconditioners and Krylov methods and the other algorithmic components. They all work in effectively the same way. So Newton methods are our workhorse nonlinear solver. And the main thing to understand from the perspective of this presentation is that the user code here has a nonlinear function, and you as an application are responsible for evaluating that nonlinear function. And then our code for the nonlinear solver will handle everything else. So going back to our picture here of the flow of control of an application, this is a case where the nonlinear solver needs to interact with the user code for function and possibly Jacobian evaluation. So we have callback functions that handle that. So when using a nonlinear solver, you call SNES set function to indicate the code that will do that function evaluation, and likewise the Jacobian evaluation. And you can provide whatever information you need through a context variable. So the PETSc software never sees the application data or that other information. It's just a pointer that's passed so that you as an application can do whatever you need. So here's more specific details on how the user-provided function actually would look on your end in terms of implementing it. So we take as input the current solution vector, as output the residual or nonlinear function. Again, the user context that passes application-specific information. Likewise, the Jacobian routine that you as an application provides has a similar setup there, where as input you take the current solution vector, then we indicate data structures that would be used to store the matrix, and optionally a different matrix to use for preconditioning. It's not required to use a separate matrix, but some applications choose to do that. And here you also can indicate whether the non-zero sparsity pattern of the Jacobian matrix will stay the same throughout multiple nonlinear iterations, or will be changing, because we can get better performance if we exploit things that remain the same throughout multiple iterations. So as alternatives to the application computing a Jacobian, there's a built-in capability for a sparse finite difference approximation using so-called coloring. So what that does is makes multiple calls to your function evaluation code in order to build up the Jacobian information. That's a great way to get started if you want to use a method that requires derivatives, but you don't have derivative code handy. Because writing it, as any of you who've done it know, it's very tedious and labor-intensive and error-prone. There's also support for automatic differentiation capabilities, which can provide code based on your function to compute derivatives. So now layered on top of the linear and nonlinear solvers are time integrators. This slide shows the various ODE forms supported. So we can think most generally by the top equation there that shows we have a function g that is a function of time and your unknown x, and also the spatial derivatives of that, x dot, is equal to some other function f, which is a function of time and the unknown x. Sometimes in a more simplistic form, we consider a mass matrix that's showed by the third equation there, mx equals f. And if there is the mass matrix is just identity, then we have the simplest form shown in the bottom equation. So the user who is solving an ODE then provides these callback functions for time integration using the three commands below. So basically, they're going to be providing a right-hand side function that would be to evaluate the function x part. That's a part where f indicates the part where you would generally be using an explicit type method. Don't necessarily need to use an implicit part. Whereas the g part on the left-hand side of that first equation is the part of the function where you would want an implicit solver, where for some reason you need implicit algorithms. So we can provide both f and g, and then optionally also the Jacobian of the function g. So I alluded to explicit and implicit methods. Carol Woodward will talk about this in much greater detail, but basically explicit methods for time integration are relatively easy and accurate, but it challenges that they must accurately resolve all timescales. So they're not good for stiff problems. On the other hand, implicit methods are much more robust and can handle stiff problems, but they're harder to implement and they require linear solves. So the combination that blends these two together is called implicit-explicit methods. And so they enable you to tackle different parts of your problem that are amenable to explicit and implicit approaches. So these are often good choices for multiphysics applications where you have different kind of behaviors and different regions of your problem. So the interface that I showed here is set up to make it easy for you to do that in your application code. This slide shows just a few of the examples of time-stepping methods that we have. In your PDF file, if you click on the green highlighted part at the bottom, you'll see the full list of options. So there's a variety of Runge-Kutta methods that are really the workhorse of much of what we do, and then a variety of other choices here. We won't go into the details due to time constraints. Part of what's important to understand is that you want to think about what you're doing holistically. This diagram here shows that in practice, you have many, many choices at all layers of the algorithms that you're using for a problem. We advocate that applications interface to PETSc at the highest algorithmic level that makes sense for your problem. So in particular, in many cases, interfacing at the time-stepping level is the best choice. And then underneath, PETSc can automatically do some smart things to pull together other aspects of algorithms and data structures, but yet at the same time, you as an application have the ability to customize choices at runtime for those lower layers as well. So it's important to keep in mind that experimenting with algorithms is very, very critical. there's no way to get optimality in what you're doing without an interplay between the physics of what you're modeling and what the algorithms are set up to handle well. So we can do that by using flexible programming. It's important not to hardwire algorithms and data structures, but really set yourself up so that you can make choices as you learn more about your problem, as you evolve your problem to tackle harder physics and other aspects of functionality. Another key point is that it's very important to work with your real code that has all the gory details of what you're modeling. It's also useful to experiment with simplified models, but we really are set up to handle things that are much more complicated, and the code is really, in the end, going to run much better if you experiment with those choices in the context of your full simulation. As Satish will discuss in a few minutes, it's important to profile your code as you're building it up and working with it. So within PETSc, there's capabilities to automatically build up that profiling and use it very effectively. So we already talked about how PETSc is structured so that as an application code, you just call it as a library. So it doesn't seize control of your main program, and it doesn't control the output. It propagates everything up to your main program. It also propagates errors from underlying packages. And then you indicate the communicator where you want to call the library. So it's possible, if you have an existing code, that you might find it useful to incorporate existing data structures and algorithms that you already have for functionality so that you could, say, compare those with some of the others provided in the library. That is all possible using the various capabilities for so-called shell matrices and shell preconditioners. So that would enable you to wrap your existing functionality and then call it through the PETSc interface. So for example, if you have a matrix data structure that you want to use, you can then call that through the higher level nonlinear solvers and whatnot by using this approach. We can also directly use memory that you've allocated for vectors and matrices by calling these commands here. For example, vet create MPI with array will then not allocate fresh array space, but will use the array that you provide to it. PETSc provides a uniform interface across multiple languages, and again, you have a choice about the level of abstraction that you use when you're interfacing to the software. Higher is generally better from our perspective. So along that vein, it's great to take advantage of other software packages out there that already provide higher levels of abstraction. And here's a list of some functionality provided by external software teams that can leverage PETSc. So for finite element modeling, finite volumes, eigenvalues, wave propagation, micromagnetics, et cetera. There are a lot of choices, and it's great to take a look at what's out there. And from those, you can still have access to all the algorithmic customizations that we just talked about here. One aspect that I'll talk about in more detail next is numerical optimization within the Toolkit for Advanced Optimization, or TAO. While previously this had been an external package, it's now considered to be part of TAO. Part of PETSc, rather. It's distributed with PETSc. And the developers for that functionality are Todd Munson, Jason Sarich, and Stefan Wild. So the TAO package focuses on nonlinear optimization problems. It can optionally support variable bounds or complementarity constraints, and some support is also provided for PD-constrained applications. So basically, TAO provides a suite of iterative nonlinear optimization algorithms. Generally, each iteration computes a search direction, and then the function values and gradients are calculated until various conditions are met for convergence. Newton-type methods, quasi-Newton methods, conjugate gradient methods, derivative-free methods are all provided, and in different circumstances, various choices make a lot of sense. One area that has received a lot of attention lately are derivative-free methods, which would be a good choice if you have a very expensive function evaluation. So for example, if your code for a function evaluation takes 100 hours to run, you probably don't want to compute gradients, which are first derivatives, and Hessians, which are second derivatives, because the time would be prohibitive. So in that case, a derivative-free option may be a good choice to consider. Here's a list of the various solvers available in TAL, and the manual pages for TAL is provided in that link, have a lot more information. So I'm just going to briefly touch on distributed arrays, which represent our topology abstractions. We talked earlier about building up matrices and vectors, and we need some way for those linear algebra objects to talk to meshes or grids. So DM is the part of PETSc that handles that, and it provides a way for interfacing between the so-called grid and the vector. So it can provide support for helping with parallel data layout, refinement and coarsening, and transfer of ghost values, as well as matrix memory pre-allocation. So briefly, we have support for a couple different approaches. DMDA is the support for Cartesian meshes. So these are logically regular meshes that are very nice for simple finite difference problems, and some of the examples that you'll see today use those. DMPlex is more general topology that can handle any dimension. It's more complicated, but more flexible. DM Composite enables us to pull together multiple DAs. This is important for multiphysics support. And then we also have DM Network, which is useful for discrete networks such as power grids or circuits, and DM Moab, which is an interface to the Moab unstructured mesh library that Vijay will talk about this afternoon. We don't have time to go through these in detail, but we'd be glad to chat with you offline, or you may want to go to the manual pages as indicated here. So basically, the Distributor Ray, which is our logically regular support, enables us to help handle transitioning between the parallel layout and the local layout that's used for evaluating, say, nonlinear functions. And it also can help with refining meshes and hierarchies. So we looked at this diagram before that shows what we mean by local nodes given in red and ghost nodes given in blue. And I won't go through the details for how the distributed array works, but on your own time, you can take a look at the slides. Basically, the main point is the distributed arrays help orchestrate transitioning between a local view to each process and the global view, which is used for our vector and matrix and solver objects. Next, we'll just talk about performance. So we've gone to great effort to put together lots of functionality for solvers that we can compose in different ways. How do you determine how well you're doing? I expect that in earlier parts of this program, you've already talked about scalability, where these diagrams show what's looking good for strong scalability as well as weak scalability. And depending upon what your goals are, you want to be considering both of those. One thing to keep in mind is that here's a quote from Bill Gropp, who I know spoke earlier this week. Bill was a founder of our PETSc project, and he pointed out that the easiest way to make software scalable is to make it sequentially inefficient. And of course, we don't want that. None of us wants that. We want efficient software. So in order to be able to really function efficiently and understand what your program is doing, you need a performance model for what you're doing that takes into account memory bandwidth, latency, various algorithmic parameters, et cetera. In order to fully understand where to focus your time when we're trying to do better with your code, it's important to have a performance model. So we don't have time today to talk about that or go into details at all, but there are some slides online at the PETSc website if you're interested in learning a little bit more about performance modeling. And I know some of our other speakers later in the sessions will address that. So I just want to make it clear that it's important for you as an application person to understand the details of what your code should be doing, so that as you begin to profile and understand performance, you know if you're doing reasonably well or if you have opportunities to improve. Okay, so now we're going to switch gears, and Satish will talk about some of the mechanics of debugging and profiling.
Thank you, Lois. Lois covered most of the mathematical aspects of the library, but when you're developing your application, usually you have to deal with software development, and PETSc has some inbuilt tools to help with that. Normally, we expect users to develop software on the laptops or workstations, and then once the code is developed and debugged, you would run on the big machines. So some of the tools we have inside PETSc are useful when you're developing on your laptop. On the big machines, I am sure some of the topics of debugging have been covered, but this is a glimpse of a basic feature of PETSc which helps you with starting a debugger. As Lois indicated, PETSc can support a lot of command line options to switch between various functionality. And one of the features we provide is the option start in debugger. With sequential debugging, it's usually easy to just run the debugger in your application, but the challenge is to when you're running parallelly and trying to debug, it's not so easy unless you have access to a parallel debugger. And PETSc kind of provides you a way of accessing a parallel debugger in the sense that it spawns a debugger session for each and every process you might be running parallelly, or you can choose a subset of processors you want to debug. Say, for example, you're running on 64 nodes, and you want to figure out what's happening on node 2 or 3. You can use the option debugger nodes 0 or 2 or 3, and then the debugger will be spawned only on those 2 nodes. Usually, you get a debugger window on Xterm so that you can control it. And we support various debuggers, GDB, LLDB, and so on and so forth. And sometimes on clusters, it's not easy to debug without the parallel debugger. So as long as you can forward an X display, you can still do it because our default debuggers spawn through Xterms. PETSc also has a lot of error checks all over the code, so that many times there's a error within the library. PETSc error handler is called. Usually that's handled by the function PETSc error. So if you're running code in a debugger, you would just put a breakpoint in the PETSc error routine, and then you would see where exactly the error happened. If not, PETSc error is used to print a stack trace on the screen so that you get an idea of where exactly the error happened. The other aspect of PETSc is we keep track of most of the memory allocated within the library, and using the functions PETSc malloc and PETSc free, which have wrappers on the basic system malloc and free. And then we have some extra macros which can check if there is any memory corruption by checking the bounds of the allocated memory using PETSc malloc and PETSc free. So the check memq macro can be used by user to throw the code to see if there is a corruption at any given place. But with better tools available right now, like Valgrind, much of this functionality is not needed. We strongly recommend our users to use Valgrind to figure out any memory corruption issues. Once the code is Valgrind clean, then you can use it on big machines. Usually, Valgrind is available on a Linux or a Mac machine, but not on big machines, I guess. PETSc also collects performance statistics of most of the components, and we provide a simple interface to accessing most of the performance statistics. Log view is an option which provides that. It gives you information about the timing of various routines, the flops that might have been invoked in those routines. Usually it's a manually computed thing using the function PETSc log flops, and also memory usage to some extent, because all memory that is allocated using the PETSc malloc PETSc free is kept track of, and also all the MPI message sizes and number of calls to MPI message communication primitives. So the profile provides a glimpse of the application behavior in all these aspects, so that one can look at them and figure out if there is some abnormality that you don't expect that's happening inside their application code. Users can also create their own events for the user part of the code to get a summary of those statistics. And we provide PETSc log event begin and PETSc log end functions so that you can wrap your own routines that can be listed in this summary. We can also split up the application to multiple stages so that you can profile each stage separately. For example, when you're using multiple solvers for different parts of the code, you would like to get different summaries for each of the solvers so that you can just look at those separately. This is a sample printout from one of the applications and gives you a glimpse of what kind of data the logs view shows you. It can show you the summary of number of objects that are created, the flops that have arithmetic flops that the application used, and then a performance metric flops per second, and then number of messages from MPI, message lengths, and the number of reductions in each of those stages. And this is a more detailed view of a performance for a given application. It shows you a lot of data, but I just would like to point you to a few basic things. Like for each stage, each function, it gives a summary of number of times the function is called, maybe the time taken, and then the percentage of time in that stage. For example, if you look at one of the routines like SNES solve, which is halfway down, it shows like it's taking maybe 50% of the runtime in that one. There are 4 calls to it, and that's taking 50% of the runtime for the whole application, which means that there's 49% of time taken by some of the parts of the code which is not the linear solver or a nonlinear solver. So when you run and get this statistics and see that the nonlinear solver is taking just 20% of the time, it means that you should be looking at optimizing something else than trying to optimize the solver. So it gives you a basic idea of what to do next. It also lists the flops at the very end, and then some idea about the communication in the different stages. So if you look at one of the fields is like global and stage. The global gives you the total for the whole application, and the stage is like if you use the stages for that particular stage, it gives you the statistics for that. And within that, there is a time, there is a percentage of flops and percentage of messages and reductions and lengths. So to some extent, sometimes when you're running parallelly, the computation routines might take more time, and sometimes it could be the communication routines that may take more time, especially when you're running a big number of nodes. You might see that the cost of the communication routines might go up, and then the percentage of time in those communication routines go up, and that's usually reflected in some of the communication routines. These are some examples of routines which might have communication, like vec dot, vec m dot, vec tom, which have reductions in them, and that can show up in the log summary. And when you see that, you might have to figure out, oh, maybe there's something else I might have to do if that's the primary cost of the whole simulation, or maybe it's something else. So when you have these numbers, it gives you a better idea of where to look for the bottlenecks. As conclusion for the tutorial, we can help you with solving algebraic and DA problems. We hope that PETSc can provide an efficient way of getting your code running parallelly. And then we provide support and help and discussions through our mailing list. The PETSc uses a mailing list which you can use, or Maint is a way of contacting us with bugs. And then if you have encountered any bugs or documentation issues, you can send us that, and we'll try to fix those things as we can. And if you have extensions to PETSc, we gladly accept contributions. A lot of our users keep sending us fixes as patches or pull requests, new features as pull requests, and we gladly accept those. And this is a link to our website where most of the documentation and other information is available. As mentioned, our user list is active. You could subscribe to the users list and monitor that what kind of discussions are going on, or we have searchable archives for a users list where previous discussions are available.
This is a question actually for you or anybody in the audience. Do you have debugging requests where people want reproducible results to help them debug?
Reproducible results. What we tend to do is the log view which I showed is more like a has a lot more information than the performance statistics. It shows the compiler options and so on and so forth. So it's more, and also the snapshot of the PETSc library, which is used for that run. So it's more like a snapshot which hopefully can provide a way of replicating those results in the future.
So I was referring to the fact that when things happen out of order, you get different floating point errors. And because floating points
Yeah,
not
there's definitely interest in that. If Mike Haru, who's a leader in that community, will speak during dinner on Monday about the importance of reproducibility. So we're certainly working towards that within our library and also in collaboration with some other folks in other projects. So, an important topic.
If I am incorporating PETSc in my existing MPI code, so like how will it connect with my existing communicator? And
That's a great question, and one that in a general sense we can answer here, but we encourage you to talk one-on-one with Satish or me later. As we pointed out, you as the application person had the ability to call the PETSc library with whatever communicator you want to use. So you could use it for your whole application or part of your application, and really that's up to you. So you provide the communicators when you create the objects, so when you create the vectors, matrices, solvers, and whatnot. So you have a lot of flexibility.
So this is a short question. In the last slide, you showed that you can do profiling and provide the flop count and the timing for the program. But if you're providing the function, for example, the shell function, we are doing the program conditioning, is that?
Then you as an application person would need to provide counts of flops and whatnot if it's not something that is written within the library itself. And there's an interface to support you providing information for your user parts of the code.
So it's not like cover count?
No. So there's a function called PETSc log flops. You would count your arithmetic in your loops manually and then call this function to log it, and then that number is registered within the logging infrastructure, and the log summary will get that information from this place.
So this is intended to provide support in a way that makes it easy to understand how the various objects fit together, and that is really the reason for this aspect of profiling. It also makes sense to use complementary profiling capabilities developed elsewhere in the community for other aspects of profiling. So this is really intended to give you a view of what's happening in the different objects within the overall code.